Picture a dense, rigid piece of agricultural waste, like maybe a discarded palm frond or a tough stalk of bamboo just lying on the ground.
Right.
Now, to traditional commercial agriculture, that is a huge liability. It requires energy to move, it takes up space, or you have to burn it and create emissions.
Yeah, it's just trash to them.
Exactly. But I want you, the listener, to zoom in on that wood fiber, like closer than the human eye can see.
Down to the microscopic level.
Right. You are looking at this matrix of billions of chemical scissors.
Which is such a crazy visual.
It really is. And these invisible tools are systematically snipping apart the incredibly complex molecular bonds of that rigid wood.
Just completely dismantling it.
Yeah, taking apart an otherwise indestructible biological polymer piece by piece.
And, it is a fundamentally different approach to waste. We aren't talking about physical degradation here.
Like grinding it up.
Right. Or thermal degradation, like throwing it in a fire. This is ancient, hyper-targeted biochemistry. Mycelium, which is the vegetative part of a fungus, it's executing this exact evolutionary program that it developed over literally millions of years.
Wow.
Yeah, to extract energy from compounds that bacteria and insects just simply cannot penetrate.
And that biological mechanism, that's the engine for the entirely automated, high-margin food and energy ecosystem we are unpacking today on this deep dive.
It really is the core of the whole thing.
So we're looking at the operational framework of Ecoladang microfarms, specifically their high-value controlled environment agriculture systems, which they outline in their EMF Pillar 3 on mushrooms.
Right.
The mission here is to deconstruct how integrating this highly specialized fungi with sovereign AI-managed climate pods creates a farming loop that operates with zero waste.
Which sounds impossible, but the sources break it down perfectly.
They really do. So let's start with the economic premise, because Ecoladang is actively rejecting the standard farming playbook here.
Oh, entirely.
There are no commodity crops in this portfolio. You're not going to see, vast warehouses of standard white button mushrooms.
Right. And the underlying logic there is purely market-driven. Because commodity agriculture, by definition, is a volume game.
Low margins, right?
Exactly. Razor-thin margins. You are basically attempting to outscale global competitors while remaining entirely exposed to, macro fluctuations.
Right.
Like supply chain issues, logistical overhead, crazy price wars.
It's a race to the bottom.
It really is.
Yeah.
So by pivoting exclusively to high-value specialty varieties, the operator completely insulates themselves from that race.
That makes total sense. And the sources show they divide this high-value target into two distinct categories.
Yep.
You have the edible gourmet market on one side and the medicinal, nutraceutical market on the other.
Right. So on the gourmet side, we are looking at premium Shiitake, blue oysters, and lion's mane.
Oh, lion's mane is so popular right now.
It's huge.
Right.
And then on the medicinal side, the focus shifts to strains like Reishi, alongside that same lion's mane, which is amazing because it has this massive dual-purpose demand right now.
You can eat it for dinner or take it as a supplement.
Exactly.
But hold on, let me play devil's advocate for a second.
Sure.
Just because a crop is premium today doesn't mean it's immune to market saturation tomorrow. Like if everyone listening to this suddenly starts growing lion's mane, the price is going to drop.
Economics 101.
Right. So how are they protecting the value of that harvest once it actually leaves the controlled environment?
Well, that introduces their processing methodology. And honestly, this is arguably as critical as the actual cultivation.
Okay, walk me through that.
So they aren't relying solely on the fresh produce supply chain.
Because it goes bad so fast.
Exactly.
Yeah.
Fresh mushrooms are highly perishable and therefore highly volatile. You have a ticking clock the second you harvest them.
Right.
The strategy involves immediate downstream processing to convert that raw biological yield into shelf-stable, high-margin, consumer packaged goods.
I see. So what kind of products are we talking about here?
Well, think about the culinary applications of these specific fungi. The sources mention a few really interesting eating methods. For instance, they can be shallow fried to preserve that really delicate texture.
Oh, nice.
Or, and this is a massive trend globally right now, they're frequently fried with a salted egg batter.
Oh my gosh, salted egg batter is amazing.
Right. It creates this incredibly complex, savory snacking profile. It's wildly popular.
I would buy a bag of those right now.
Totally. And the mushrooms are also robust enough to hold their structure in industrial soups and stews.
Okay, so they're versatile.
Very.
Right.
But the most economically efficient processing path, the one that really drives value, is reducing them to umami powders.
Okay, let's drill into that for a second. We toss the word umami around a lot on cooking shows, but biologically, what are we actually extracting there?
That's a great question.
Like, why does a ground-up mushroom command such a premium as a flavor enhancer?
It all comes down to glutamates and specific ribonucleotides. Mushrooms are naturally just packed with L-glutamate. It's an amino acid that literally binds to specific receptors on the human tongue.
And that signals the brain.
Yeah, it signals this deep, savory, meaty flavor.
Wow.
So when you dry and grind a premium mushroom like a shiitake, you are aggressively concentrating those glutamates.
So it's like a natural flavor bomb.
Exactly. And furthermore, the drying process itself often increases the levels of naturally occurring guanylate.
Guanylate.
Yeah, it's a nucleotide that works synergistically with glutamate.
Okay.
So when they combine, they multiply the intensity of that savory flavor exponentially.
That is fascinating. So you are basically converting a crop with, what, a 2-week shelf life?
If you're lucky.
Right, a 2-week shelf life into a highly potent, shelf-stable biochemical flavor enhancer.
Exactly. And food manufacturers will pay an absolute premium for that natural umami.
Because everyone wants clean labels now, no synthetic stuff.
Right.
And for the snacking segment, you mentioned the salted egg batter, but the primary mechanism the sources talk about is industrial low-pressure frying, or vacuum frying.
Yes, vacuum frying is key here.
I really want to understand the thermodynamics of this because traditional deep frying, it destroys a lot of the nutritional value we just talked about, right?
Absolutely.
Especially the delicate compounds in something like lion's mane.
It absolutely ruins them. But the physics of vacuum frying solve that exact problem.
How so?
Okay, so at standard atmospheric pressure, water boils in 100 degrees Celsius, right?
Yep.
To drive the moisture out of a mushroom and make it crispy in a traditional fryer, you have to submerge it in oil that is far hotter than 100 degrees.
Like 170 or 180.
Usually around 170 to 190 degrees, yeah. And at those temperatures, you trigger massive thermal degradation.
Right, you're just burning off the good stuff.
Exactly. You destroy heat-sensitive vitamins, you warp the complex polysaccharides that actually give medicinal mushrooms their value in the first place.
Which defeats the whole purpose.
Exactly. And you trigger excessive Maillard browning, which can result in these bitter, burnt flavors.
But if you drop the atmospheric pressure...
You drop the boiling point of water.
Oh, wow.
Yeah. Inside a vacuum fryer, the atmospheric pressure is significantly reduced. So water will boil and evaporate out of the mushroom's cellular structure at temperatures as low as like 60 or 70 degrees Celsius.
That is wild.
Right. So you achieve the exact same rapid dehydration and crisping effect, but the oil is barely hot by traditional standards.
So you're not cooking it to death.
You're not. This preserves the molecular integrity of the medicinal compounds. It maintains the natural cellular structure and the color of the mushroom.
So they still look good in the bag.
Exactly. And importantly, it dramatically reduces the amount of oil absorbed into the final product.
Right. It fundamentally changes the product from this greasy, heavy snack into a preserved, high-nutrition crisp.
Precisely. It's a completely different product matrix.
Okay, so we know what they're growing, and we know how they're processing it to maximize the profit. But getting back to the actual farming part.
To physical infrastructure.
Yeah. Cultivating truffles instead of iceberg lettuce, basically, that requires a completely different approach. You cannot just put highly sensitive reishi in an open field and hope for the best.
No, the wild weather would destroy it.
Right. So Ecoladang uses what they call sovereign infrastructure built around this modular agri-shack system.
Yes. The physical architecture is entirely decentralized.
Meaning what, exactly?
Well, instead of a massive monolithic warehouse where a single atmospheric contaminant can blow through the HVAC and ruin an entire season's yield.
Which happens a lot in commercial ag, right?
All the time. Instead of that, the production is isolated into distinct, purpose-built agri-shacks.
Okay.
So a franchisee might have a cluster of these shacks on their land,
Yeah.
and each one serves a fundamentally different biological or mechanical purpose.
Let's trace the life cycle through these shacks then. It begins in the inoculation hub. This is an entire agri-shack dedicated purely to introducing the mushroom genetics into the sterilized growing medium.
Right.
And the sources say they do this from either spores or live plant tissue cultivated in agar dishes.
Yeah, agar cloning is very common for these premium strains.
But why dedicate an entire structural unit just to this one step? That seems like overkill.
Well, because inoculation is basically a battle of competitive biology.
Oh, okay, I like that phrasing.
Yeah.
Yeah.
The substrate block you are trying to inoculate, it's essentially a highly nutritious buffet.
Right. It's just pure food waiting to be eaten.
Exactly. So if you expose that buffet to open air, ambient mold spores, wild yeasts, and bacteria will instantly land on it.
And they want to eat it too.
Yes. And those contaminants reproduce exponentially faster than complex fungal mycelium does.
Wow.
If a single trichoderma spore, which is a very aggressive green mold, if one of those lands on your agar dish or your substrate block during inoculation, it's over.
Just one spore.
Just one. It will completely overrun the premium mushroom strain.
So an inoculation hub is essentially a positive pressure clean room.
Like in a hospital or a microchip factory.
Basically, yeah. It utilizes HEPA filtration and laminar flow hoods to ensure the air moving over the work surface is entirely devoid of microscopic particulates.
Okay, so the franchise owner is operating a sterile laboratory, essentially.
Yes.
That seems like a massive technical barrier to entry for someone who just wants to operate a high-yield farm. I mean, you're asking a farmer to suddenly master sterile microbiology and agar plate transfers?
That's a very fair point.
Yeah.
And that introduces a crucial structural advantage of the Ecoladang network.
Okay.
The average grower does not actually have to operate an inoculation hub.
Oh, they don't?
No. The network allows highly specialized franchisees to focus entirely on that highly technical inoculation phase.
Ah, I see.
Yeah, they master the sterile lab work, they create these perfectly colonized, contaminant-free substrate blocks, and then they supply those robust blocks to other growers in the network. So they act as basically the seedling nursery for the rest of the ecosystem.
Exactly.
So if I am a typical farmer operating the next module in the chain, which is the fruiting station agri-shack,
Right.
I bypass that high-risk microbiological phase entirely.
You don't have to touch an agar dish?
I just receive a fully colonized block. The mycelium has already established dominance over the substrate, so it's highly resistant to outside contamination at that point.
Precisely. Once it's fully colonized, it's like a fortress.
Right. So I just focus on the environmental triggers that force that block to produce the actual mushrooms.
And in a fruiting station, the physical geometry of the shack changes completely.
How so?
Well, you aren't working on flat, sterile tables anymore.
Yeah.
You are utilizing vertical rack scaling.
Going floor to ceiling.
Exactly.
Yeah.
The goal there is land-independent expansion. You want to maximize output per cubic meter rather than square meter.
Oh, that makes sense. You're farming the volume of the room, not just the floor space.
Exactly.
We should also note the sources mention a third type of agri-shack, which is dedicated entirely to processing.
Right, keeping it separate.
Yeah, once those vertical racks are harvested, the fresh yield goes into this dedicated space for fresh packing, vacuum packing for transit, the dehydration we talked about, and that low-pressure vacuum frying.
It keeps the messy, organic harvesting and processing completely out of the highly sensitive growing areas.
Which is just smart risk management. But let's stay in the fruiting station for a minute, because managing those vertical racks introduces a massive logistical problem.
Oh, huge.
Let's say I'm growing two different crops. A blue oyster mushroom wants a highly humid, warm environment.
Very tropical.
Right. But a premium Shiitake often requires a cold shock, like a simulated autumn temperature drop, just to initiate pinning.
Yes, it needs that trigger.
So if I have a single fruiting shack, I can't provide both climates simultaneously in the same room.
You can't. And that limitation is exactly what their integration of artificial intelligence solves.
Okay, this is the AI part.
Yes. The fruiting stations are populated with what they call edge fungi nodes.
Edge fungi nodes. Sounds like a sci-fi movie.
I know, right? But specifically, these are the AI mushroom fridges developed by their primary partner, 7-Star Mushroom.
Okay.
These aren't just open shells in a room. They are isolated microclimate pods managed by an AI system.
Let's break down the computing architecture here, because the term edge is really important. They rely on edge computing rather than a centralized cloud system.
Yes, and the distinction is critical.
Right, because in a standard smart greenhouse, you have an IoT temperature sensor that, it pings a server in a data center hundreds of miles away.
Yep, somewhere in the cloud.
That server runs an algorithm, decides the room is too hot, and sends a signal back to turn on an exhaust fan.
And the friction there is latency and connectivity dependency.
If the internet goes down, you're screwed.
Exactly. If your internet connection drops, or if Amazon Web Services experiences an outage, your highly sensitive agricultural environment begins to degrade immediately.
The fans just stop turning on.
Right. But when we talk about edge computing in these 7-star fungi nodes, the processing power, the localized artificial intelligence, is physically sitting on the motherboard inside the fridge unit itself.
Okay, so it doesn't need to phone home.
No. The sensor data is analyzed instantaneously without ever leaving the physical location.
Which is critical because the variables they are balancing are incredibly volatile.
Extreme.
We are talking about strict minute-by-minute management of temperature, humidity, and CO2. I think most people assume plants and mushrooms function similarly, right?
They do, and that's a huge misconception.
Right, plants inhale CO2. But a massive rack of fruiting mushrooms is constantly inhaling oxygen and off-gassing carbon dioxide. They breathe like we do.
Exactly. So the CFM, the cubic feet per minute of airflow, becomes the most critical metric in the entire system.
Because if you don't exhaust that CO2...
If you do not actively exhaust it, it pools in the lower racks because CO2 is heavy.
Oh, right.
And mushrooms grown in high CO2 environments become visibly deformed.
Really? Like how?
They develop these really elongated, stringy stems and tiny underdeveloped caps. They look like aliens.
Wow.
And that renders them completely unsellable in the premium market.
A chef isn't going to buy that.
No way. However, here is the thermodynamic trap. Every single time you turn on an exhaust fan to clear that CO2
And
out.
blowing out the moist air.
Yes. You are simultaneously stripping the humidity out of the pod.
And mushrooms are, what, upwards of 90% water?
Exactly. So if you drop the relative humidity too fast, the fruiting bodies just abort. They literally dry up and stop growing.
But if you overcompensate and spike the humidity without proper airflow,
then water droplets pool on the mushroom caps, and that instantly invites bacterial blotch, usually Pseudomonas, which ruins the crop overnight.
oh my gosh, so it's a tightrope walk.
It is a constant, localized thermodynamic balancing act. It's incredibly difficult to do manually.
So the Edge AI handles all of this.
Right. It is utilizing pulse width modulation to constantly adjust ultrasonic misters and variable speed exhaust fans in real time. It's actually predicting environmental drift based on the specific biological growth stage of the strain inside that exact pod.
Because a baby mushroom needs different humidity than a mature one.
Exactly. And because these are isolated nodes, you can run entirely different climates directly adjacent to one another.
Inside the same agri-shack.
Inside the exact same room. You can run a cold shock protocol for Shiitake in pod A while running a high humidity, warm, tropical environment for lion's mane in pod B.
That is just incredible. That effectively decouples the yield from the geographic location and the macroclimate.
Yes, geography doesn't matter anymore.
You are synthesizing perfect, specialized microenvironments on demand. But, an environment is just an empty space.
Right.
The biological fuel, the actual calories the mycelium is consuming to build these mushrooms, that has to come from somewhere.
It needs food.
Right. Which brings us back to those microscopic chemical scissors we talked about at the very beginning of the deep dive.
Yes, the core biological mechanism.
So, to understand this zero-waste loop Ecoladang is building, we have to look at the substrate, the physical medium the mushrooms are actually grown on.
Right.
In traditional agriculture, inputs like fertilizer and feed, they represent massive recurring operational expenditures.
It's the biggest cost for most farmers.
But the Ecoladang model utilizes local, low-value agricultural waste as the primary input. We are talking about fibrous, processed palm fronds or bamboo.
Which is brilliant because it's abundant and basically free.
But wait, palm fronds are notoriously difficult to compost. They take forever to break down.
Oh, they are incredibly stubborn. They're highly lignified.
Lignify.
Yeah, from lignin. It's the organic polymer that gives wood its structural rigidity. They give it like the rebar inside concrete.
Okay, that's a good analogy.
It forms this dense, complex armor around the cellulose in the wood, making it basically impenetrable to most bacteria and normal agricultural pests.
Right, you can't just plant a tomato seed in a pile of crushed palm fronds and expect it to grow.
No, it would just sit there and die. The vast majority of microorganisms lack the enzymatic pathways to break down lignin. It is the three-dimensional, highly irregular polymer. It's tough stuff.
But mushrooms are different.
Very different. Specifically, white rot fungi, which includes many of our premium gourmet varieties, they have evolved to secrete specific extracellular enzymes.
Okay.
Primarily lignin peroxidases and manganese peroxidases.
And these are the chemical scissors.
Exactly. See, the mycelial network doesn't have a stomach. It digests its food externally.
That's so alien.
It really is. It pushes these highly reactive enzymes out into the surrounding wood fiber. And the enzymes literally cleave the carbon bonds within the lignin molecule.
They just snip the rebar apart.
Exactly. They dismantle the structural armor, breaking it down into simple, soluble sugars that the mycelial network can then easily absorb and metabolize.
Wow.
The fungi are basically mining energy from a biological matrix that is entirely inaccessible to the rest of the agricultural food chain.
That is just a masterclass in biological efficiency.
That's elegant.
You take a regional liability, like literal mountains of palm agricultural waste, and you convert it into the foundational energy source for a premium crop.
It's the ultimate upcycling.
But I do have a major point of friction here that we need to address.
Okay, let's hear it.
The documentation we reviewed explicitly states that while they use local waste for many varieties, their primary partner, 7-Star Mushroom, actually imports pre-inoculated substrate logs specifically for the Shiitake crop.
Yes.
And they import these from a reputable supplier all the way in China.
That's right.
Doesn't shipping heavy logs of wood across the ocean completely defeat the entire purpose of localized zero-waste agriculture? I mean, the carbon footprint alone.
It is a totally valid critique regarding the carbon footprint, but it reflects a very deep understanding of biological realities versus, well, idealistic farming.
What do you mean?
Well, Lentinula edodes, which is a true Shiitake mushroom, it evolved in East Asia. And it evolved growing specifically on the dead wood of broadleaf trees, things like the shea tree, oak, and chestnut. Its enzymatic pathways, those specific chemical scissors, they are highly optimized for that specific lignin profile of those hardwood trees.
Ah, I see. So it's a picky eater compared to something like an oyster mushroom.
Highly selective. While an aggressive blue oyster mycelium might just rapidly devour the lignin in a local palm frond without missing a beat.
But Shiitake wouldn't.
No. Forcing a premium Shiitake strain onto that same palm waste substrate results in dramatically lower biological efficiency.
It just doesn't grow well.
The yields drop significantly, the cap morphology is poor, meaning they look weird, and the time to harvest extends way too far out.
And that ruins the economics.
Exactly. From an enterprise utility perspective, if your goal is consistently hitting the premium gourmet market, you simply cannot afford subpar yields just to satisfy a localized input philosophy.
Right. You are balancing biological optimization against logistical costs.
Precisely. By importing these perfectly optimized pre-inoculated hardwood logs from experts in China, they guarantee that those AI fungi nodes are operating at maximum yield efficiency for that specific crop.
I get it. So they let the oysters and the lion's mane eat the local palm waste because they're fine with it, but they bring in the heavy artillery for the Shiitake to ensure perfect batches because Shiitake is just too difficult to grow on less favorable substrate.
Exactly. You have to play to the biology.
But regardless of whether it's a palm block or an imported Chinese hardwood log, eventually those chemical scissors run out of material to cut.
The buffet closes.
Right. The block flushes its mushrooms, you harvest them, and you are left with this depleted block of sawdust and mycelium.
Yeah, the spent substrate.
In any other normal farm, that block is compost at best, or it just goes to a landfill at worst.
And that transition point right there is where the true circular economy of this system activates.
Okay, tell me how.
We have to look at the biochemical state of that spent substrate block. Remember, the fungi have spent months saturating that material with peroxidases.
The enzymes.
Yes. The rigid lignin polymers, that rebar we talked about, it has been completely shattered. What was once a tough, indigestible palm frond or dense oak log is now soft, highly friable, and structurally compromised.
The fungi have essentially pre-digested the agricultural waste.
That's exactly it. They have unlocked all the remaining carbohydrates, and that pre-digested matrix becomes the primary zero-cost feedstock for the next phase of the ecosystem.
Which is the insect farming unit.
Exactly.
Okay, let's dissect the economics of commercial insect farming for you guys listening, because it's fascinating.
It really is.
If you are raising black soldier fly larvae, for instance, to produce high-value insect protein for animal feed, your single largest operational bottleneck is the cost of feed.
You're just constantly buying commercial feed to sustain these larvae, which severely compresses your profit margins.
Right, and black soldier fly larvae are voracious consumers. They eat constantly.
They do, but they still require accessible carbohydrates. If you throw raw palm fronds at them, their feed conversion ratio just plummets.
Because they can't chew through the lignin.
Right, they expend way too much energy trying to break it down, or they simply cannot digest it at all and they starve.
Oh, that
But by introducing the spent mushroom substrate, you are providing a feedstock where the metabolic heavy lifting has already been completed by the fungal enzymes.
It's like baby food for the insects.
Perfectly said. It's pre-mashed and ready to absorb.
It is a cascading trophic system operating inside a few shipping containers.
It's incredible.
Think about the flow here. The farm intakes low-value local waste. The fungi extract the high-value gourmet and medicinal mushrooms from it.
Huge profit margin there.
Right. Then the biological byproduct of that harvest, the pre-digested wood, is immediately shuttled over to the insects.
Zero cost input.
The larvae convert that pre-digested waste into premium protein, which is another huge profit margin. You are generating two entirely distinct high-margin revenue streams from a single initial input of agricultural trash.
And to top it all off, the thermodynamic loop is closed by the farm's biomass pillar.
Oh, right, the energy source.
Yes, the energy required to run those AI fridges, the laminar flow hoods in the clean room, the localized edge computing, all of it is generated on-site through biomass gasification.
Wow.
It is an entirely sovereign loop.
Okay, that elegance on paper is totally undeniable. It sounds perfect.
It does.
But I have to play the skeptic here again, because agriculture is brutal.
Oh, absolutely brutal.
Hardware fails, supply chains collapse entirely. If you build a highly complex, interconnected biological and technological machine like this, you are multiplying your points of failure.
You definitely are.
If the entire network relies on 7-star mushroom to supply the AI fridges and to import those perfect Shiitake logs from China, what happens when a shipping container gets held up at port? Or when a hardware component for the AI fridge faces a global shortage?
Everything grinds to a halt.
Right. The franchisee is left with an empty agri-shack, a bunch of hungry insects, and a negative balance sheet.
That is the inherent risk of highly specialized integrations. However, the ecosystem architects at Ecoladang, they've planned for this. They mitigated this exact risk by establishing enterprise-grade supply chain redundancy.
Okay, what does that look like in practice?
Well, Ecoladang acts as the infrastructure and software provider. They're the API for farming, if you will.
I like that.
They build the shacks, they provide the AI framework, and they establish the operational standards. 7-Star Mushroom plugs into that API as the biological and hardware expert, but crucially, they are not the sole point of failure.
Because the documentation indicates they actively maintain enterprise-grade alternative partners.
Exactly. The system is designed to hot swap suppliers if needed. If the primary source for those pre-inoculated Shiitake logs faces a logistical bottleneck at the port, the network automatically routes orders to a vetted secondary enterprise partner.
So the franchisee doesn't even feel the hiccup.
Right. They are insulated from the upstream disruption. It modularizes the biological risk across multiple suppliers.
That is smart corporate resilience.
It's the only way a massive franchise network can survive.
Now, let's talk about the data layer supporting this whole enterprise architecture. Because there is a glaring buzzword in the operational framework that usually sets off my alarm bells.
Let me guess. Blockchain.
Blockchain, yes. We are talking about farming mushrooms and feeding wood waste to insect larvae. Why on earth do we need a cryptographic distributed ledger involved in this?
I know, it usually sounds like a desperate play for venture capital funding.
It really does. It screams crypto hype.
In many consumer applications, it absolutely is just hype. But in highly regulated premium B2B supply chains like the ones Ecoladang is targeting, an immutable ledger solves a massive, real-world friction point.
Which is what?
Provenance and trust.
Okay.
We are not talking about speculative cryptocurrency coins here. We are talking about utilizing the underlying cryptographic hashing technology to create an unalterable record of biological reality.
Walk me through how that actually works on the ground, practically speaking. Let's make it concrete.
Okay. Consider the medicinal nutraceutical market we mentioned earlier.
Like the Reishi.
Exactly. You are a franchisee selling a highly concentrated Reishi extract. And that commands a massive premium price based on its purported purity and active compound levels.
Right. People are buying it for their health.
So the buyer, which is likely a major pharmaceutical or supplement manufacturer, they require absolute certainty that this reishi was grown under strict operational parameters.
They need to know it's not full of heavy metals.
Right. Free from contaminants, and they need to verify it is indeed the exact specific premium strain you promised, not some cheap knockoff.
So how does blockchain prove that?
Well, the edge computing nodes we talked about earlier, the AI fridges,
Yeah.
they aren't just adjusting the fans and the misters. They are constantly hashing the environmental data.
Oh.
Precisely. The minute-by-minute temperature, the exact humidity, the precise CO2 levels, the origin data of the specific agar plate that mushroom was cloned from, the exact time of harvest in the agar shaft.
It's recording all of it.
All of this data is cryptographically signed at the local edge node and committed to the distributed ledger immediately.
Wow.
So when that vacuum-packed bag of dried reishi moves from the franchisee to the central processor and then finally to the B2D buyer, the entire chain of custody and its complete environmental history is fully auditable and immutable.
You can't fake it.
You can't.
Yeah.
It prevents a bad actor in the network from just taking a subpar commodity mushroom they bought down the street, putting it in a premium Ecoladang bag, and selling it at a massive markup.
Because the ledger would show there are no environmental logs for that batch.
Exactly. You can't fake the environmental logs because they were hashed locally by the AI fridge in real time.
That provides absolute, undeniable proof of quality.
And in the premium medicinal market, proof of quality is essentially currency.
That makes total sense. It's not about crypto, it's about undeniable auditing.
Yes. Furthermore, it automates the highly complex accounting of a franchise network.
Oh, how so?
Well, think about the web of interactions. If a franchise owner uses an alternative partner's logs and they process those mushrooms in an Ecoladang AgriShack, which is managed by a 7-star mushroom AI node.
That's 3 different companies involved in one mushroom.
Right. So the blockchain smart contracts handle the fractional revenue splits instantly and transparently upon the final sale.
Nobody has to sit there with an Excel sheet figuring out who owes who.
Exactly. It is the digitization of trust. It allows a highly decentralized network of independent farmers to operate with the logistical cohesion of a massive multinational corporation.
Man, it really is a phenomenal synthesis of disciplines when you step back and look at it.
It really is.
I mean, we started this deep dive with the sheer biological brute force of fungal enzymes snipping apart the molecular armor of dead wood.
The chemical scissors.
Right. Then we moved into the fluid dynamics and edge computing required to perfectly balance microclimates in real time without the cloud.
Yeah.
We explored the thermodynamic efficiencies of vacuum frying to preserve complex polysaccharides without burning them. And we watched the biological relay race hand off that pre-digested palm waste to black soldier flies to generate a secondary protein yield.
It represents a total paradigm shift in how we view agriculture.
It really does.
We're moving away from the industrial era of agriculture,
Yeah.
the era that relied on brute forcing massive amounts of synthetic inputs and chemical fertilizers into the soil.
And destroying the topsoil in the process.
Exactly. We are exiting that era and entering an era of hyper-optimized, biologically driven precision.
It fundamentally proves that massive profitability and absolute sustainability do not have to be mutually exclusive.
They can actually drive each other.
By using technology not to, conquer nature or pave over it, but to perfectly manage and accelerate these ancient biological pathways, we can extract immense value from what the rest of the world just considers trash.
And, the implications of this extend far, far beyond just agriculture.
Oh, absolutely.
The underlying mechanism here, utilizing highly specific fungal enzymes to dismantle indestructible polymers, that is actively being researched across multiple scientific disciplines right now.
Because if they can eat lignin.
Exactly. If mycelium can be programmed and environmentally optimized by an AI edge node to effortlessly tear apart the lignin in a dense palm frond, it forces us to look at our other industrial waste streams.
Like what?
Well, what happens when we identify the precise fungal strain and the perfect microclimate required to break down complex hydrocarbons?
Like oil spills.
Yes, or as synthetic plastics, or even forever chemicals like PFAS in our water supply.
Wow. You're saying we could train fungi to eat our most toxic pollution?
If we can build the right AI climate pod to support the right fungal strain, the biology is capable of almost anything.
That is the true frontier right there.
It's mind-blowing.
We are just scratching the surface of what these chemical scissors are capable of when guided by precise computation.
We really are.
I love that. So, to everyone listening, keep pulling at those threads. Keep questioning the systems around you. And the next time you see a discarded piece of wood, or honestly an empty plastic bottle, consider the microscopic machinery that might one day consume it.
It's a great thought to leave on.
Thanks for joining us on this deep dive, guys. We will see you on the next one.